Okay, we're ready to begin this morning's session, and it's a great treat for us to have Lance Dixon from SLAC, who's made remarkable contributions to new ways of calculating using Feynman diagrams, reorganized in very creative ways. And he'll be talking about 7 decades of particle scattering from Feynman diagrams to the LHC.
Thanks a lot, Frank. And thanks to all the organizers, and especially Lars Brink, for the opportunity and the privilege to come speak at this remarkable conference. It's been really great, very stimulating, great to interact with so many people who are in Feynman's orbit at different semi-major axes or whatever. And also to see all the students who are learning about his legacy. And one aspect of Feynman's legacy was how we think about particle scattering everywhere. And it influenced and underlay a lot of the discoveries that led to the Standard Model and to the current exploration of the Standard Model at the Large Hadron Collider. So I want to take you along some of that story. But first I should mention that the way I knew Feynman was maybe similar to how Mike Kreutz did. That is, I was also an undergraduate at Caltech from 1978 to 1982. And I took 2 courses full-time and a shorter one from Feynman while I was there. But the first time I met Feynman was at freshman camp. So back then, the little freshmen, they showed up and they got bussed off and then taken on a boat to Catalina Island, which is a little island offshore from LA. And it was kind of rustic. And I remember a bunch of us wannabe theoretical physicists as Feynman groupies. We were all hanging out in a circle. There were about 10 or 20 of us, I don't know, quite a few, sitting cross-legged on the grass. And Feynman was there in shorts and a kind of safari hat type of thing. And we were all trying to pick gleams of his wisdom. And that certainly, I already thought I might want to do theoretical physics, but that was certainly a big inspiration to me. So let's see. I want to tell you a little bit about what Feynman diagrams did for quantum field theory in the early days, and then discuss how they came to be part of testing the most precise theory, or constructing and then testing the most precise theory ever, quantum electrodynamics. And after discussing that, I want to talk a little bit about Feynman's role in the early days of QCD, and then talk about QCD at the LHC, which is another computational problem in which reorganizing the Feynman diagrams, as Frank alluded to, has been very fruitful for making further progress. And it also tells us something about particle scattering in other theories. And I should make a disclaimer, which is I'm not a historian, and half of these 7 decades happened before I entered graduate school. And some people here know the history better than I do, so they should interject or provide clarifications later if I get something wrong. So Feynman's revolutionary insights into quantum theory and scattering and relativistic theories were initially for this theory QED, which he wrote a book about later, The Strange Theory of Light and Matter, or how electrons, that is the simplest charged particles we know, interact with the quanta of light, or photons. And having these 2 quantum fields, it's not the whole universe, but it's a very precise setting where we can now compare experiment and theory to parts per trillion, which is really remarkable. And this conference was alluded to in the earlier discussions. It was called the Shelter Island Conference, and this is like 2 years after World War II ended. A group of physicists got together to talk about quantum theory. This was Willis Lamb. He had just discovered this 1,000 megahertz shift along with Rutherford, between the 2s and 2p states of hydrogen, which wasn't accounted for in the Dirac theory. And also there, but not in this picture, was Isidore Rabi, who reported on something that could be interpreted as the electron, an anomaly in the electron magnetic moment. There was also J. Robert Oppenheimer, who led the team at Los Alamos. This is Feynman here with the pen in his right hand. And Julian Schwinger, who he would share the Nobel Prize with later, is looking down at these scribbles. And, and I don't know everybody. This is Abraham Pais, who would later write a biography of Einstein as well as contribute to quantum theory. Weisskopf is definitely there. That's Weisskopf probably. And I don't know, people, I don't think that was Panofsky. I forgot who it was, but it's definitely not Panofsky. we can go through it later or look back up again. Yeah.
This is 2 years before II Rabi in the UNESCO conference declared CERN as the plan.
Yeah.
The reunification of Europe and its competition with the United States technologically and scientifically. And that's how CERN was born by II Rabi.
Yeah, Rabi played a huge role in the creation of CERN. That's right. And this is just, we heard a little bit about this before. Feynman sort of wrote up his thesis into this Reviews of Modern Physics article where he proposed the space-time approach to, originally to non-relativistic quantum mechanics. But by this time, he was well underway. By the time this came out, he was well underway on the relativistic case. And he set forth the path integral, which we heard about earlier, and how path integrals really come to life in the context of lattice gauge theory, where you can evaluate them without using Feynman diagrams, exactly in some sense. But also, that brings me back to the second time I encountered Feynman, which was we took the 2-year course of freshman physics, and at that time, Feynman wasn't teaching it, but he did come in when it was time to get our first exposure to quantum mechanics. And so we were basically, he didn't say that, but we were learning path integrals before we ever saw the Schrodinger equation. So it was a pretty inspiring introduction to the field. And then there were a pair of papers that came out in early 1949, but many people knew about what was going on before that, in which he outlined the beginning of this new formulation of relativistic quantum field theory and displayed the first Feynman diagrams. What I want to explain here is how different that was from the way people were thinking before, and Pierre already touched on some of this, but basically, before Feynman, everything was discussed in a very time-ordered way. You have a Hamiltonian, you evolve it, there are interactions. If you had wanted to draw graphs, although people really didn't, you could have drawn graphs describing them, but everything the interactions had to be strictly ordered in time. But what Feynman realized, this is just another way of saying some things Pierre said probably, is that in relativity, time ordering is not a very consistent concept, because depending on the frame, I should have shown this frame moving this way, but if this frame is moving differently, these two events that happen here, if they're far enough apart, they can appear in a different time ordering in the other frame. And so if you have a quantum process and you describe something happening here and something that happens here, maybe you should think about uniting it with another case where they happen in different time orderings. For example, a photon could come in over here, collide with an electron, transform into a sort of excited electron or a state of the electron field, which could then split into a photon and an electron. But a different observer would see something happen quite differently. And when this electron comes in this case, the photon would have to do something first, and it would split into what was going to be a positron, taking into account Wheeler's interpretation of positrons as electrons running backward in time. And so Feynman realized that in some sense these contributions should be lumped together into a single entity which had a single Feynman diagram covering both cases. And so that's sort of the essence of how he covariantized or made relativistically invariant, made consistent with special relativity, the quantum theory of electrons and photons. And he had a great line in one of the papers where, well, this was just a little bit after World War II, so he thought about a bombardier flying low over a road who sees 3 roads. And then only after flying a bit longer does he realize that it's really just one road with a zigzag in it, the path of the electron moving backwards in time and then continuing on. And so that would be a more holistic way to treat things. Now I want to talk a little bit about the mass shell. So the mass shell is a condition that particle theorists always talk about that describes what you need to satisfy if you want a particle to propagate all the way out to infinity in a scattering process. And the familiar equation we've seen already, E equals mc squared, that's just a piece of a little more general equation. This corresponds to a particle that is at rest with 0 momentum. But Einstein actually wrote this equation here, that E squared is p squared plus m squared. You can put the factors of the speed of light in here if you want, but from now on we'll just take them to be 1. So if p is 0, we recover E equals mc squared, or just E equals m. We set c equals 1. And also Einstein told us that the energy and the momentum should be combined into a relativistic 4-vector. So there's the energy, we call that the p0, or the time component of the 4-vector, and then the spatial momentum p are the other 3 components. And these mix together in the same way that time and space mix when you do a Lorentz transformation. But there is something that's left invariant, which is E squared minus p squared. Or when we write it in Lorentz index notation, p mu, and we often just abbreviate that as p squared. So there's this invariant combination of the energy and the momentum, which according to this equation is just the mass. But that's only satisfied by what we call real particles. Of course, before Feynman, we didn't really call anything a virtual particle. But after Feynman, he had lines going through the middle of his diagrams, and those lines did not satisfy p squared equals m squared, so we say they're off-shell. So there are very special conditions for particles that can fly off to infinity on the outside of the scattering process. Those are on-shell. And then the virtual particles are off-shell. And we'll come back to this in the later part of the talk, because what we try to do is reformulate the theory so that more and more particles can be put on-shell. Because these off-shell particles, they're a little more convention-dependent, let's say. And they're, of course, an incredibly useful device for calculating. But sometimes there are other ways to go. Now, in order to put these 2 diagrams together, Feynman had to develop a new propagator, and Pierre talked about this already, so I don't need to say too much about it, but it's pretty clear that if you want both those diagrams together, you have to be able to propagate signals both forward and backward in time. And so, in fact, you have to propagate positive frequency signals forward, positive energy signals forward, and negative energy signals backwards. And we usually write down all these scattering amplitudes in momentum space, and so there was a kind of propagator this is actually for a scalar, not for an electron, but it's close, which propagates signals forward. And in order to do that, there's a prescription for how you do some integral, and that's where there's a famous I epsilon that appears. But it appears in a kind of clunky way in the retarded propagator, so that you cannot write it in a very nice, simple, covariant way. There's also the advanced propagator, in which you flip this sign. And then the Feynman propagator, you can see it's much more elegant because you don't have to show P0 and capital P separately. All you have to show is this relativistically invariant combination of them. And so by combining these diagrams and arranging the causality to be in this neither advanced nor retarded system, he could have a causal and yet relativistically invariant description of each diagram. Now, an important person in this game was Freeman Dyson. It's a shame he couldn't make it here because he played a key role in unifying three different developments that were going on at the same time, which were due to not only Feynman, but also Tominaga and Schwinger. And he sort of explained the unity of them. And ironically, his paper came out before Feynman's. And so in some sense, the first Feynman diagram in print actually was in Freeman's paper, although he acknowledges, of course, that he got all the ideas from Feynman. Anyway, he demonstrated the equivalence, and in particular, he considerably noticed that the Schwinger theory could be considerably simplified, basically by using Feynman diagrams. And from that point on, I think most people used Feynman diagrams to work out similar problems. And there's this great write-up that Freeman gave, which was presented in the art science folder, where he compared himself to Ben Jonson and Feynman to Shakespeare, because the two elders, separated by 6 years and 9 years in the two cases, served as incredible mentors. And Shakespeare actually acted in Ben Jonson's first play, which I think is analogous to this. And then Jonson wrote about Shakespeare in his obituary. Nature herself was proud of his designs and joyed to wear the dressings of his lines. And, well, Freeman obviously knows his Shakespeare. So we saw this Feynman diagram already, and it's the most iconic Feynman diagram, partly because it's incredibly versatile. We'll see it come back again and again, where the same diagram represents not just electron-electron scattering, but electron-quark scattering, beta decay, just dressed up, where you change the identity of these lines a little bit. And this diagram is so famous that it's even been carved into rock in Tuva. And this is a friend of mine who was also a friend of Feynman's and Ralph Layton's. And they were arranging to go to Tuva towards the end of Feynman's life. Anyway, Glenn made it to Tuva to see he's also an Atlas experimentalist. So he made it to Tuva to see this Feynman diagram, et cetera. Another thing that Feynman did in the first two papers, which, it doesn't bring as much it didn't sort of reformulate things in as great a way, but it turned out to be incredibly important for the quantitative evaluation of these diagrams, was just this little trick here where he showed that if you have two things in the denominator, you can rewrite them as an integral over one thing in the denominator. And this trick gets used over and over again by people from graduate students doing quantum field theory to people at the cutting edge state of the art. That's one approach to evaluating the integrals that you have to do in Feynman diagrams. So now I want to turn to a specific application of Feynman diagrams, which is the one that leads to the most precise comparison of theory and experiment anywhere. And that is the electron anomalous magnetic moment. And the title of my talk was about scattering amplitudes. This is a little weird. When you put an electron inside what's called a Penning trap, in order to measure its magnetic moment, it doesn't really look like a scattering process. Instead of bringing something in from infinity and sending it out again, what you actually do is you trap this electron for a long time. It circulates around. It has a few different excitations of a basic circle, and you can measure this frequency. And the other thing not shown here is that the electron has a little spin, and the magnetic moment has a characteristic kinematic factor, and then a pure number called the gyromagnetic ratio, G sub E, in front of it. And this was 2 in the Dirac theory, and Robbie was finding evidence that it was not quite equal to 2 at the Shelter Island conference. And when it's not quite equal to 2, then when the electron precesses, it makes maybe 2 plus a little bit more precessions every time it goes around the circle. The spin rotates a little bit differently. And so you can measure these frequencies incredibly accurately. That's what clocks are good for. Frank talked about clocks that are good to the 10 to the minus 18. The electron is 2 clocks at the same time. It's the one for the spin frequency precession and then the orbital. Actually, they use multiple clocks based on the orbital motion, so they have a few frequencies. And they can extract by counting at different rates, which is the most precise thing you can do. You can measure this GE extremely accurately, as we'll see. So anyway, this setup doesn't look at first like a scattering process, but in fact, the important thing, this G sub E, can be extracted from a type of scattering process. It's kind of a limit of a scattering process where you take this momentum kick and you make it as gentle as possible. You take the photon here, which could come from another electron or some other source, through the magnetic field, and you just let it just barely affect the electron scattering. Okay, so that's the thing that a theorist does to compute this G sub E, tries to evaluate this amplitude with 2 particles here and one more very soft photon here, very small photon. And so then Feynman told everyone how to do this. You draw all the Feynman diagrams with a specified incoming state and outgoing state. So the first thing that happens is you just have a direct interaction with the electron line of this photon. But then you start adding these lines for virtual photons. And I didn't draw all the diagrams. There's some other ones where instead of 2 virtual photons, you have a loop inside at the 2-loop level. And you have to put in factors for each of the vertices and each of the lines. But in particular, each vertex gives you a factor of E. So this one has 1 E. This has 3 E's. And this has 5 E's. This one also has 5 E's. And at each order, there are more and more of these diagrams that you can draw. But it would have been way worse in time-ordered perturbation theory, where you would have to also sum over factorially the number of different ways of putting these lines in there. And so this is an incredible simplification. And in QED, you're very fortunate that each loop is suppressed by a big number. Each loop comes with an extra E squared, and if we divide it by 4 pi h bar c, we get a universal constant called the fine structure constant. And because it's so big and it often actually gets another pi, every loop is about 500 times smaller than the previous loop. So you can get a long ways with a few loops. However, you have to evaluate more and more of these diagrams with each additional loop. So this is the universal third-order contribution to A mu. Well, that's the muon. Actually, it's the same as in the electron. There are some non-universal terms. They're generally a little bit smaller. And at least in the electron case, they're very small. But this is basically the number of diagrams you have to evaluate. But you would have to multiply by about 7 factorial if you didn't have this ability to combine all different time orderings in one. And so without that, it would be hopeless. Now, even with Feynman diagrams, this is a difficult problem. And it took decades to get to this order. But it wasn't necessary. And the current state of the art is 2 loops past that. It's 5 loops, and there are 12,672 Feynman diagrams. So now people don't draw every single Feynman diagram, unless maybe they're trying to draw a picture of Feynman or something. But they draw sets that are related by something called gauge invariance. So the number of gauge invariant sets is actually a lot smaller. And the most difficult set is this one here. These circular loops, those are all additional loops of virtual electrons. This one has only virtual photons. And it's the most complicated one to evaluate. In fact, they're still evaluated using Feynman parametrization. And then you resort to numerical integration at this order. And that's been a program. The 5-loop has been going on for about 12 years now. And Toichiro Kinoshita has spent his entire career working on basically this problem. So now I can show you 7 decades of one particular baby scattering amplitude all on one slide. And the first term is known as the Schwinger term because Schwinger worked it out first in 1948. And it took quite a while Well, it was first calculated by Karplus and Kroll, but they made a mistake. And there were some possible disagreements with QED for a while. But then Peterman and Summerfield recalculated it and found this answer here. And they could actually do it all analytically. So you see it has some rational numbers in it. It has some factors of pi. Actually, it's always pi squareds, and a log 2, and what we call a Riemann zeta value, zeta of 3. And then, from then on, the vanguard was always numerical. So this next term was first obtained numerically by Kinoshita and Predrag Cvitanovich, 1972. And then 24 years later, the analytic formula was worked out. And it's actually not dumb to work out the analytic formula, even if you only care about the number, because these numerical integrals are very hard to do, and they didn't always agree. Subsequent evaluations were not always exactly the same. There's, I think, a 1% or 2% shift from the first evaluation to this one. But again, Kinoshita was always in the vanguard of producing the numerical results, and now they have got a good numerical estimate of even the 5-loop term. And Laporta is coming in behind, and he has made this one almost analytic. At least he's reduced it to sets of integrals, so he could give you 200 digits of this if you wanted to see them. And then there's, in the electron case, this is almost the whole story. There's a small piece from virtual loops of muons and taus and some hadrons, but it's pretty small and under control. So the theory is there, and all of this was necessitated by experimentalists. These clever experimentalists figured out how to improve this measurement by many orders of magnitude over the years, from when, well, there was a Cush-Foley experiment soon after Rabi's, and you see there were subsequent experiments up until 1970. So I need to show 2 plots, one up to 1970 to show the incredible reduction in error here. And then a second plot which shows, well, it actually jumps to 1987. And then at Harvard in 2008 was the, as far as I know, the last and most precise number, which is given here. So you can see all of these decimal places and the 0.28 part per trillion. So this number then is to be compared with this formula once you plug in a very precise value of alpha. If it's not a very precise value, it's not useful. Or you might say it determines alpha. So now the interesting thing is that in the past year or two, there's been a new measurement of the fine structure constant in cesium. And so this is the current best measurement of the fine structure constant. So you plug it into that formula and you compare it with the experimental number. And, well, they're pretty close, but they're not exactly there. In fact, there's a 2.4 sigma discrepancy. So the difference between the two anomalies is 87 times 10 to the minus 14 with these errors. So I should say that if you try to measure the distance between the Earth and the Moon to the width of the human hair, that's 10 to the minus 13. So that's the kind of precision we're talking about here. It's like, yeah, got to put this in human units, like the Tyrannosaurus Rex coming in the window of the Feynman's house. So this discrepancy is opposite in sign to a discrepancy that's caught the imagination of particle theorists for about 10 or 15 years. And that's the discrepancy for the muon. Now, the muon's a much more complicated story on the theory side because QCD actually plays a big role in understanding the last digits of the theoretical uncertainty. So this has a 3.7 sigma discrepancy, and it's in the opposite direction, which maybe makes it a little, well, it would be interesting to think if 2 different kinds of physics could explain both. And if you think there's a paper proposing that, for example. So anyway, it's still an open question whether these discrepancies really represent something new or just some little glitch, because these are very difficult calculations, very difficult experiments, or it could just be statistics. In fact, there's a new experiment on the muon that's going to report next year from Fermilab, and so people are watching that. So QED is definitely still around, still kicking, and still trying to provide information about fundamental physics. But now I want to switch from this very gentle collision where we just click the electron, tick it a little bit, to where we do incredible damage to it. So if electrons had feelings, as we heard about yesterday, SLAC would never have been built because it rips them out of their birthplace and accelerates them to the speed of light and then some. And this is a scene from when SLAC was built. So it's about 2 miles or 3 kilometers long. This is now known as Interstate 280. The director of SLAC convinced them to build the bridge first before the rest of the freeway, so that when they built the bridge, it wouldn't damage, all the vibrations wouldn't mess things up. So this was a bridge to nowhere for a couple years. And then at the end of the LINAC, the electrons were bent and slammed into a target in this large building, which was called End Station A. And well, it wasn't so clear that this was really the intention of SLAC, but there was a prime experiment at End Station A that was going to look at this, the structure of the proton. And Feynman also played a big role in that, as we'll see in a second. Now, before SLAC was built, quarks, or aces as George Zweig called them, were proposed, but it was still an open question whether they were real or maybe just a mathematical tool to represent some of the symmetries of the low-lying hadron spectra and other properties. So SLAC had enough energy to look inside the proton and see if there were hard things inside. And this is the experiment there. I'll just show you one picture. This is a spectrometer. The target's over here, and they could move these around on rails. It was designed to only look at one thing, the electron, and ignore the debris from the proton when it was broken up. And there's another spectrometer out there. So using that, they could take data at different angles and different energies. And I stole some of these slides from a talk by Marty Breidenbach, who was on these original experiments, who gave a talk this summer at SLAC on this. And what the early experiments found was something called the deep inelastic structure functions. Deep inelastic means the electron gives up a lot of energy when it hits the proton. And here time is going this way. So the electron is bouncing off the proton through a Feynman diagram with a virtual photon, and it's striking a quark, which comes out this way. And you don't really look at what happens here. Instead, you just look at what happened to the electron. But there are two variables in this. There's a virtuality of the photon, or how far off its mass shell it is, called q squared. And the more virtual it is, the shorter distances you're seeing. And then there is another variable which involved the difference between k minus k prime, that's q, and the dotted into the momentum divided by q squared. And this is called a scaling variable. B.J. Bjorkane at SLAC had proposed that there would be a reason for why this structure function should not depend on q squared and only depend on omega, later called x. So here it is for omega equals 4, and everything was very flat, indicative of this Bjorkane scaling. But BJ, as he was called, even though he was at SLAC, the experimentalists still didn't really understand what he was talking about. And here it is in the words of Marty Breidenbach. Many of us didn't understand his motivation for scaling, but then Feynman visited SLAC, and he'd been thinking about hadron-hadron interactions. And he had this model, the parton model, and he instantly understood what was going on when he saw this weak q-squared dependence of these deep inelastic structure functions. And he basically said, you have these partons inside the proton. These lines here represent the partons, and they have some probability of, we'll call f sub n, of having a fraction x. So that was called Feynman x, although in deep inelastic scattering, sometimes it got called Bjorkane x. Anyway, when they have this fraction x and this probability, then you could calculate this Feynman diagram, and you could work out the relation between this probability and these structure constants. structure functions. And so he could, and the fact that there's no q squared in here, this is the electric charge, but there's no q squared, that's the essence of scaling in a nutshell. And with that same Feynman diagram, the same one we saw for electron scattering, just turned on its side and dressed with some different overall factors, you could also learn about the spin of the things inside the proton. And Callan here developed the Callan-Grose relation, along with David Grose, that said, well, there are actually two of these structure functions if you work things out, but they're related when you know what the constituents are, at least a leading order when you can neglect, or a large X where you can neglect gluons. And so the Feynman diagram, so Kurt did actually learn what Feynman diagrams were later in his career in order to provide the relation that led to the conclusion that these partons at least had the right spin to be identified with the quarks of Gelman and Zweig. Furthermore, after that, this scaling led to a search for theories that would have a property. I probably left off one very crucial point, so let's go back here for a second. These partons are imagined to be interacting with each other because they're bound into a proton. The point is that if there's some limit at short distances where the interactions get very weak, then this virtual photon probes things at short distances and short times where there's no time for any other interactions. And that's the whole rationale for being able to use a diagram here with a free quark in it to work out this behavior. So that fact that you can use a diagram where you neglect the quark interactions inside the proton, that was a principle known as asymptotic freedom. And Frank, together with David Grose and David Politzer, understood that that came out of non-abelian gauge theories. And then Harold Fritsch, who's here, worked with Gelman to find a specific example of a non-abelian gauge theory where the gauge group was SU3, that is the number of colors of the quarks was 3, and that became quantum chromodynamics. And Steve Weinberg also worked on that. So pretty soon after this time, especially aided by the November Revolution of November 1974, people started to understand that there was a non-abelian gauge force binding things into quarks into hadrons like the proton. Just to go back a bit, I don't need to say much about this slide because we heard a lot of discussion about it yesterday. This is the one paper, well, the main paper that Feynman and Gelman wrote together where they, through their shotgun marriage, where they exposed the V minus A or left-handed structure of the weak interactions, and there was also important work by Sudarshan and Marshak around the same time. So this put the L into what we now call SU2L, that the weak interactions only talk to left-handed fields.
Why do they say with the fact that 2 to the 10 to the minus 4 pi, the very last sentence, very last phrase, starting with the width?
That's a good question. I don't know. I would thought that's what it would predict a small branching fraction. I don't know the answer. I'll have to look that up later. Okay. I don't know. So then this gauge group for the weak interactions was extended to SU2 cross U1 by Glashow, and a more complete version of that became the Weinberg-Salam or Weinberg-Salam-Glashow model in the 60s, including neutral currents, which we now call a Z boson. And the charged currents they were talking about here were W bosons. Actually, in their paper, they explicitly state that there's no evidence for neutral currents, so we're not going to put any in. Okay, they kind of missed that one, but there was no data to guide them, not even wrong data. So, and then the Higgs mechanism was added in 1964. And eventually, we arrived in the late 70s at the standard model, where the quarks inside the proton, U and D, were supplemented by heavier quarks, and the leptons charged and the neutral ones, neutrinos, made up of all of matter. And the force carriers, apart from gravity, are shown here. And the only thing missing, waiting for the, well, the top was found in 1994. And then the Higgs boson, the one spin 0 particle we know, was found in 2012. So, but this theory gave finite testable predictions for all quantities. And most of the predictions were made using those Feynman diagrams. And it was really well established by the time I started getting into the game in the early 1980s. Here you can see the three subnuclear forces, electromagnetism, weak and strong, and their basic interactions between charged particles of matter are through these vector boson carriers. But this same diagram, the sort of kinematical part of it is exactly the same for all of them. These gauge interactions are quite universal. The strength of them depends on the theory and exactly how they talk to different particles. So it's so simple you could teach it to a dog, right, Lars? Okay, so now we're going to fast forward to the 2010s and the advent of the LHC at CERN outside of Geneva. This is a machine which Maria will probably say a lot more about, but it's a massive undertaking, 27 kilometers around. For this purposes, there's two detectors that look for the shortest distance effects, Atlas and CMS, on opposite sides of the ring. And it makes particles that can't be made anywhere else. And case in point is the Higgs boson, which was discovered now 6 years ago, but many of its properties still need exploring. And it's going to accumulate up to 20 times many collisions by the end of its lifetime, as it has already. So this is a typical LHC collision. So it looks a little bit different from just taking that electron and kicking it slightly. It places a different premium on theory. You don't need to get to 10 to the minus 13 because Maria is not there yet. About a 10 to the minus 2, maybe, yeah, basically 10 to the minus 2. Sometimes 10 to the minus 1 is plenty good enough. But there are many, many different kinds of processes, and they're more complicated with many X particles coming out of them. Here are those two incoming protons. Here are two partons that happen to be close enough to each other to collide. And this is what we call the short distance collision. And this is the piece we can actually compute the best. But it's sort of buried in this whole cloud here. And coming out of here are jets. We have models for these jets, parton shower models of the kind Rick Field worked on early on. And then we also have we have the structure of the proton, those Fn of x's, the parton distribution functions, which we actually know quite well. So the outer part we have to model or get from experiment, and the inner part is calculable in principle. And the question is, how do we best calculate it? This shows a plot of cross-sections, and it's just the very most basic cross-sections that people study at hadron colliders, moving from the Tevatron to the LHC. And the LHC has run at several energies. And the higher you go in energy, the higher the cross-sections get, because you can sample the partons where their distributions are larger at smaller x fractions. And down here is the Higgs boson, and this plot was made before we knew the mass. So many different lines for possible masses of Higgs bosons are shown here. Now the amount of data the LHC has collected is so much that you can get down below this line. You can see things that are so rare at in some sense it is parts per trillion, but it's rareness rather than precision. Also, all these processes, well, there are many more that are studied experimentally. And every time you have a basic process, you also can make it with additional jets, because there are quarks and gluons flying around all the time, and those particles emerge as jets in the detector. So that there's this enormous background of all these jets. It's just a huge haystack. And you're looking for stuff way down here. It's like a needle buried inside this haystack. So you need to understand the haystack as well as you can in order to find the needles inside it. And this is just the two energies that the LHC has run at so far on the vertical axis. 8 TeV, that's 8,000 times the mass of the proton. or 13,000 roughly. So this principle of asymptotic freedom that we just discussed is that the gluon's sort of anti-screen charge in an opposite direction to what happens in QED. And so the force becomes weaker at shorter distances or higher momentum transfers of probes. And the LHC, its collisions are basically operating out here, or we can arrange things so that this part is calculable. This is the part that Mike Kreutz talked about yesterday, where it's confining. We can't really use a perturbation theory in alpha S, and we use lattice methods to describe the structure. But from now on, we'll talk about sort of this distance scale. But it's married with a longer distance scale, the structure of the proton. And so what we do, which is a generalization of what Feynman did in the parton model, is we factorize the process into pieces. And we, because of this impulse approximation, we sample partons one at a time. And so we can write probability distributions, which are measured by experiment in conjunction with some more theory there. And then we calculate something which we can think of as what happens in the femto universe, way inside a proton, where quarks and gluons are almost free. And so then we go off and do this calculation and multiply it by these factors. And so this is the part that we want to calculate. It's a function of amplitudes for scattering, complex quantum amplitudes. So basically, once we know that, we know how to get numbers out for experiment. And we have to do an expansion in this small coupling. And we can now do leading order quite reliably. And there has been a breakthrough in doing things at next to leading order. But in some cases, we need to go to even higher orders in this alpha S expansion. Because the leading order is incredibly unreliable. When we go to next to leading order, we have of order 15 to 20% uncertainties. And in the cases that we can get to this one other order, we get down to this level. And there's some cases where you want to go even further if you can. So why do this? Well, one of the rationale for the LHC is to search for supersymmetry using the Razor variable or other methods. But so the dream is that we might be able to make dark matter in the laboratory. And this is how we would make it. We would probably make it by making another particle first, one that has color, so that it has a large production cross-section. One example is supersymmetry, but it doesn't have to be that. But there's a partner of the gluon in theories of supersymmetry that is produced very copiously, but it has to decay to dark matter. And it has to get rid of its color in QCD by making jets. So you get 4 extra jets in this kind of way of making dark matter. And in order to see dark matter at the LHC, you can't see it directly. You only see it because it leaves the detector and the events look imbalanced. So that imbalance we call missing transverse energy. And in this case, it would come along with 4 jets. And here we see an event from Maria's detector, CMS, which has 5 jets, even better, and it has a huge transverse momentum sum of the jets. And also this missing energy is also enormous. So that looks perfectly like making 2 gluinos. The only problem is that the standard model does the same thing too. So the standard model contains in it this neutral weak carrier, the Z. And 20% of the time, the Z just disappears. It decays into neutrinos. And they escape from the detector. So this is what we call an irreducible background. That means you can't tell on an event-by-event basis whether you're talking about supersymmetry or something in the standard model. So you need to calculate the standard model and make sure you're not seeing more events than that. And 10 years ago, you could only do this at leading order. And then the normalization was quite uncertain. Now we can do it at 1 loop higher. So this blob represents all the Feynman diagrams that have no loops inside them. And that's the leading order of the approximation, just like in QED. And the next order includes virtual corrections like this and some other things, but you need these blobs where every Feynman diagram has to have one loop in it. So I put a hole in the blob. So now we can reduce these uncertainties. But in order to do that, Feynman diagrams were not the best way to go. So the problem is that here's like one of the diagrams you would need. Well, this would be a Z plus 5 jets. You have a quark and gluon coming in. You have a loop of, and a lot of these gluons interacting. But these gluons, they make a lot of Feynman diagrams. In fact, they make 256,264 more diagrams. So maybe that's not the best way to do this. In fact, there are very subtle symmetries of these interactions which you cannot see through Feynman diagrams. And we want to take advantage of those. So I sort of said this before, but the leading order of the approximation is tree level. And trees can be simple, or with lots of jets, they can be fairly complicated. But there were actually some methods that worked pretty well for trees already. But the loops like this were the ones where the textbook methods quickly failed. For the experts, the loops alone are not enough. You also need trees with one additional gluon or one additional parton. These diagrams are infinite, not only due to renormalization of the ultraviolet, but due to infrared divergences. And they have to be canceled. But that's a solved problem now. The question is how to get these loop amplitudes. And here's the number of diagrams as a function of the number of jets in the final state. So you can see how fast it's growing. And basically the current limit that people got to with Feynman diagrams was about this level, about 2 additional jets. And now we can get to about this level, at least for these kinds of processes. Other processes that are more complicated are somewhere in between. Now, I got into this game after some friends of mine, Zvi Byrne and David Kossauer, had used string theory, which many people in this audience have worked on, like Lars and John Schwartz, puts all the Feynman diagrams into one package. So there they are all. If you know what this means, in principle, you know everything. But actually, you know too much because this has many other states in there that aren't there in QCD. Now, all you have to do to get rid of them is to take the limit as the momenta go to 0. And that led to things that were not exactly Feynman diagrams, but looked sort of like them. There are various cubic diagrams. And using those rules, my friends Zvi and David could compute a 2 goes to 2 gluon scattering amplitude in terms of helicity amplitudes. That one had already been done using Feynman diagrams, using some method where you interfere with the tree, but that obscured the structure of the helicity structure. And there was something remarkable in the helicity structure which we wanted to exploit, and that was that the tree amplitudes obeyed some very miraculous properties. Many tree amplitudes in this pure gluon case would vanish. If all the gluons were right-handed, or just one of them were left-handed. These were identically 0. Very hard to see that from the Feynman diagrams unless you knew what you were looking for ahead of time. And there were these very simple formulas in many cases. And because it was opaque, maybe there was a better thing to do. I don't have time to define these variables, but they're simple square roots of what we call the Mandelstam variables. We managed to get, using these string-based rules, to one more leg, 3 gluons. And then the thing looks kind of complicated, but believe me, it's not that complicated. And a lot of things were missing. We could actually, it was simple enough we could understand the whole structure of it on general principles. And we had these factors here that are logarithms of Mandelstam invariance, but some of them were missing. And we figured out eventually why some of the other ones were missing. To do that, we had to go back to another thread, which Feynman didn't really participate in that much, which was related to something called Regi theory and the analytic S matrix. To make a long story short, you may have learned about poles and branch cuts in the complex plane. You can exploit all of that to organize amplitudes. So you can look for branch cuts in a channel, and you can find that because one of these trees happened to vanish, this thing was 0. if you divide this up into diagrams, is not so apparent. But once you look at it this way, it was clear why things had to be 0 and why things had to be non-zero. And then you could use this as a basis for actually working out the non-zero numbers. So we had this is something that's been done many more times. You get a little more computational power. You find some patterns. You try to explain the patterns. You get some new relations. You exploit the new relations to get some more computational power. And then you go back to step 1, rinse and repeat. So that sort of thing has gone on over and over again since then. We also borrowed a theory that Lars Brink came up with called n equals 4 super Yang-Mills. When you don't know what you're doing in QCD, you go to this model and test things out there. So we could do the one-loop correction to this infinite number of legs diagram, and it has the same factor and then something which is a set of Feynman integrals. And so we try to be very environmentally correct by cutting loops into trees. We can recycle the trees and reuse them, recurse over and over again. And I think I'll probably just stop with this one kind of picture of the difference between this kind of blobby approach and the discrete nature of Feynman diagrams. When you have only a few Feynman diagrams, it's like having a few grains of sand. Well, anyway, there's sort of an identifiable job for each Feynman diagram. It gives you a different piece of the amplitude, and you kind of say, this one does that. But when you have a gazillion of them, you should think of it more like a fluid. And you should not look inside the blob, but you should move it around and see what its analytic properties are smoothly. So there is more to that story, but I'm out of time. So I will just state that it works. You can get agreement with data. This is this Z plus 4 jets process I was talking about. And these are measurements that were made by Atlas. And as a function of the number of jets, to the point that we could calculate it works fine. There are other models that aren't as quite as first principles that also work pretty well, too. And this is a list of sort of a whole bunch of benchmark measurements that have been made by Atlas, but CMS has made the same set of measurements. And you can see that they all more or less agree with the theory, which are the gray bands. And so the LHC is in great shape. And I will, since I'm out of time, I will just say that it's been a great tool. The Feynman diagrams has been handed to us, and it's really enabled all these advances in comparing theory with experiment at high energy colliders, and then the electron G-2 and many other processes. So thank you.